So good morning all of you. Today is probably the last lecture on gravitation. We have had a series of about 6 lectures. So what we did was to start with the basic conservation laws which underlie all interactions, all fundamental interactions. Then we listed the fundamental forces, and then we started looking at the most ancient and the most pervasive of the forces, namely the gravitational force. It was the first fundamental force to be discovered, and it was the first application of Newton's laws of motion, which we have also enumerated: the first law, the second law, and the third law. After that, we spent a lot of time discussing how ancient and medieval astronomers determined masses and distances of various planets and stars. Using that as an input, we also studied how, making use of Tycho Brahe's observations, Kepler was able to formulate his famous 3 laws. As I told you, the most important thing about the 3 laws was that Kepler did a great shift. He did not try to understand the orbits of the planets in a frame fixed in the rest frame of the Earth, fixed in the Earth, but he shifted it to the Sun. So that was a great shift, because for a long time people believed, especially Europeans believed, that the Earth was at the center of the universe and the rest of the universe went around us, because man was the highest creature created by God. So once the shift was done, a very beautiful pattern emerged. Earlier, Kepler had been trying to fit the orbits into so-called platonic solids and things like that, because people expected perfection in the spheres or in the motion of the planets in the celestial sphere. But once he moved to the heliocentric description of the planetary orbits, he got a very beautiful description in terms of elliptic orbits. All planets moved in elliptic orbits, and he discovered 2 more fundamental features: equal areas swept in equal intervals of time, and there was a definite ratio between the period and the radius, distance from the Sun. T squared by r cubed is a constant. So in some sense, observations and analysis spread over a few thousand years laid the ground for the formulation of universal law of gravitation. Newton exploited all this. What was missing was actually the crucial concept of a force which can act at a distance. Until that time, people believed that the only forces possible were contact forces. If I want to push something, then I better touch that object and push it. Even if I don't push it, something else should push it. Like for example, when there is a gust of air which I produce that may push an object. For example, when I exhale air with a great force, it is the air that comes in contact with a leaf or a sheet of paper and that starts moving. That was the belief. Newton not only had to formulate the concept of force in a very precise manner, that which causes acceleration in inertial frame, he also was able to introduce a not so easy concept, the concept of action at a distance. This was actually the basis for the concept of a field, which came later. So once this was done, Newton was able to formulate the gravitational law, and we are able to understand a whole lot of things. Galilean law of falling bodies, the motion of the moon around the Earth, the motion of the Earth around the Sun, motion of the planets around the Sun, motion of the satellites around planets. Not only that, making use of these laws, you can estimate masses, you can estimate distance through many, many ways, and that is something that we discussed at great length. We then looked at one of the so-called mysterious phenomena that used to take place on the Earth, namely the tidal phenomena. And in the last lecture, I worked out how the difference in the force between 2 different points on the Earth, in fact diametrically opposite points on the Earth, will produce tidal forces. Water rises, and I did not work it out completely, but I showed how such a thing happens. So I hope that you people, all of you students, have spent enough time, discussed among yourselves, discussed with your teachers, to understand more about the tides. So in some sense, it was almost as if everything under the sun, including the sun, as far as gravitational forces and cosmological objects are concerned, it was understood. So today what we are going to do is to look at gravitation from a slightly different viewpoint. All this time we have been looking at gravitation through the eye of forces, through the lens of forces. This has been fundamental. What we will now do today is to switch gears and look at the same phenomenon from another viewpoint, from that of potential or potential energy. When you put a body of mass m in a gravitational field, I will come to that. These two are not distinct from each other. In fact, they are equivalent, but from the viewpoint of analysis, they are complementary approaches. What is simpler from the viewpoint of force can become more complicated from the viewpoint of potential energy, and sometimes what is simple from the viewpoint of potential can become quite complicated from the viewpoint of forces. I will give you some examples. But before that, we should carefully understand what is the meaning of gravitational potential. Newton himself did not make any extensive use of the idea of gravitational potential. It was later mathematicians and physicists who put it into full use. Laplace, especially when he wrote his equation, and Poisson equations were written for the gravitational field. I already gave a brief introduction to the concept of potential energy through spring mass system. So I said that the force F is equal to minus kx in a way implies a potential energy equal to half kx squared. So if I remember correctly, what I did was to write the total energy, the kinetic energy plus the potential energy. I demanded that that quantity should be a constant. Kinetic energy plus potential energy should be a constant. And we have obtained the equation of motion. So let us repeat that. So this approach is a utilitarian approach. It tells you it is useful to employ potential energy, but the idea of energy is much, much deeper. We have to understand that. So what is it that we did? We defined the potential energy to be half kx squared. Remember, this x is the displacement from the equilibrium position. Equilibrium position. Then of course we have the kinetic energy, half mv squared. So if we stipulate, maybe I should use kinetic energy. If we stipulate that the total energy is T plus V equal to constant in time. So we know that when a pendulum oscillates or when a spring is oscillating about its equilibrium position, it has zero velocity at the turning points. It has the maximum velocity at the equilibrium position when it passes through the center. So what we are saying is that the change in the kinetic energy is compensated by a corresponding change in the potential energy. You raise your kinetic energy, the potential energy goes down. You raise your potential energy, the kinetic energy goes down, such that this sum is a constant. So we don't have to go from force to this energy. One way of doing that is to simply take this as a hypothesis and demand this must be equal to 0. So what do we get? This tells you that mv dv by dt, which is equal to the acceleration, this plus Kx equal to 0, Kxv equal to 0. So I have used my chain rule of differentiation. d of x squared by dt, that will give me a 2x, and dx by dt, and the 2's cancel. This should be valid for all velocities. So what we do is to cancel this, and sure enough we get the Hooke law, mv equal to minus kx. So as a mathematical step it might appear to be very simple, but conceptually there is a leap in our understanding of the nature of energy. And we should remember that this has played an extraordinary role in our understanding of so many phenomena of nature, including human physiology. It is not just physics. One way to look at kinetic energy is to say that, okay, kinetic energy is lost, for example, when the particle is moving away from its equilibrium position, and suddenly it starts gaining kinetic energy when it comes. So there is a continuous loss and gain, but that kind of a picture does not account for what happened to the kinetic energy that is lost. So it is not good bookkeeping. That is what we have. But the minute we say that there is another form of energy, namely the potential energy, and this is perfectly natural, because if I take a spring, compress it, I apply a whole lot of force, and then I put a block so that it doesn't move, everyone knows that there is enormous energy stored there. That is how we store the energy, and then the minute I remove this top, it springs back. Or for example, if I take a kettle of water, cover it fully, that is the famous experiment of observation of James Watt. A lot of people had done that, but James Watt put it to good use. So if you start heating, you are supplying a lot of energy because you are heating, and the water molecules are gaining kinetic energy. So at some point the energy will increase so much that the lid will blow off. Until that time the energy is stored somewhere, okay, within that. So that is not probably a very good example, but there what we are looking at is the conversion of some heat into kinetic energy. Here we are looking at heat into potential and potential into heat. Therefore this broadens our horizon or our understanding of what energy is, and this is but a simple example. And this principle of conservation of energy, as I told you, has played a very important role, and I will make some statements at the appropriate time. The oscillation of a spring or the oscillation of a pendulum is not very different, for example, from the motion of a ball which is thrown up. So law of falling body. So what do? This is my ground. I take a ball, I give it a certain velocity and I throw it up. So all of you know how to solve this problem, because we assume that gravitational field is a constant. Therefore the acceleration is a constant. It reaches a maximum height h. This reaches a maximum height h, and then what happens? After it reaches a height h, there it has zero velocity, and therefore it becomes the turning point. So it goes there and it comes down, and when it comes down very close to the surface of the earth, if you were to make careful measurement of the velocity, you will find, provided that air resistance is small or ignorable, or you do it in, let us say, in an evacuated chamber, the speed with which it strikes the earth is the same as the speed with which it was sent up. So there is a conservation of kinetic energy when it reached back. There was nothing that was lost. Is that okay? So we can take the analogy by the same account, and we should say that when it is going up, potential energy is increases when the ball raises, and decreases when it falls. So potential means it is not visible, but it is hidden inside. That is what we say, a person has a potential to do this. We have not yet seen that. So in some sense, potential energy is always the stored energy. It is stored in some particular way, at least in the context of mechanics. And then when it falls down, whatever is stored is brought out, and we see it as the kinetic energy. Kinetic means motion, so you are seeing it as the energy of the motion. Therefore, what we have to do is to obtain a general form for potential energy. Why did I say general form? Because when you look at the freely falling body in the Earth's gravitational field, we make the assumption that this height is very, very small compared to the radius of the Earth, and therefore we take the gravitational force to be practically constant. The acceleration due to gravity is a constant. It does not change with the height at which it is from the surface of the Earth. So we want a general form. We are not going to get into the mathematical details, although it is easy to work out. It is more important to get the concept. So one observation from Hooke's law is, let us go back to Hooke's law, because that is what you are more familiar with. If F is equal to minus kx, then your potential energy is nothing but minus F dx. I am not going to get into the nitty-gritty details of very general motion. We will assume only one-dimensional motion. So the motion is always either along the force or opposite the force. If you have a more general case, for example, a particle is free to move in 2 dimensions or 3 dimensions, then what will happen? The force may be acting in one direction and the motion may be in another direction. So we don't want to do that. So what are we saying? Basically we want to write it as minus x dx by dt into dt. For example, I want to follow what is happening. Is that right? So this is what I have in my mind. So in rectilinear motion there is no problem at all, because force is in some direction, dx is there. So if I now write minus f dx, dx is of course always a positive increment, you find that this quantity is nothing but half kx squared. In fact, f dx you will learn is nothing but the work done by the system. It is nothing but the work done by the system. That is something that you would have done in your lectures on work energy. So what I am asking you is to remember whatever you have been taught, the work energy theorem in your mechanics, and make good use of it in the context of gravitation. And I am repeating this only for your benefit, so that you will recollect, you will recall whatever has been taught there. This is not a systematic exposition of the concept of potential energy. So it works very well. In a similar manner, what we can do is to start with the gravitational force, F is equal to minus g mm by r squared, and do an integration along the line of force. Do an integration, integrate along the line of force. Line means direction of the force. Everybody knows how to do the integration. All integrations need some reference point. That is very, very important, because in your class, in your calculus class, you will be taught, or probably have already been taught, that whenever you evaluate an indefinite integral, that indefinite integral is unique up to a constant, because when I differentiate, that constant goes away. We need to do that. So what I will do is, I will give you the answer and then I will tell you what kind of a constant that I have employed, so that there is no ambiguity. That is what I want to do. So we will leave it to you as an exercise to verify. So let me give it to you as an exercise. Verify that my V equal to minus g mm by r is a good candidate for potential energy. it is convenient, although it is not compulsory, to assume at this particular point that the body of this small m, mass small m, is moving in the field of a body of this capital M. Of course, whenever we write a capital M and a small m, we mean m much less than m, so that we do not have to worry about the motion of the larger mass. So, we are having in our mind, for example, the motion of blocks of stone in the gravitational field of the earth, or the motion of the moon in the gravitational field of the earth, or the motion of the earth moon system in the gravitational field of the sun. Mass of the earth, I think, is about 10 to the power of 22 kgs, and mass of the sun is 10 to the power of 30 kgs. So, we have a factor of 10 to the power of 8, which is 100 million. So, that is the difference. So, that is the picture that we have. This does not take away the generality of this expression, but for our purposes it is enough, because if you allow the large mass and the small mass to be comparable, and if you want to write down the equation of motion, it becomes a little bit more complicated. We will have to introduce the concept of a reduced mass, and at this stage it is not required. So, let us work within this approximation. That is what I have. So, when I am writing V equal to minus GMM by R, I told you I could have always put a constant, and it is very easy for you people to verify that if I were to differentiate, then I should get the force. So, what is my force? My force is minus dV by dr. That is what we are saying, into r hat. I am not writing that. So, when I do minus dV, this becomes GMM by r, and when I differentiate, it will get another minus sign, which will tell you that it is an attractive force. So, r is the unit vector that connects the body of larger mass to the smaller mass. So, it is pushing towards it. The bigger mass is pushing the smaller mass towards it. So, that is what I have, and this is the force acted upon by the larger mass on the smaller mass. So, I can actually employ my usual notation. So, I have my larger mass, I have my smaller mass, and I am denoting the unit vector like this. That is what we have. Now, all of you are proficient, completely capable of doing the differentiation. I am not even asking you to do the integration. You can verify that this will do the job, minus GMM by R. So, what about the constant? So, in order to understand the constant, what we are saying is that look at the limit r going to infinity. So, we are asking what would happen to the potential energy of the particle. So, this is the small mass, the big mass, this is my small mass, this is the distance between them, and I am asking what will happen to the potential energy as r goes to infinity. Now, the expression for the force tells me that the force goes to 0. It is the inverse square law. Now, imagine that a particle is at rest far, far away from the mass. So, for example, we see all the great stars in the sky, we see the Milky Way in the sky. They contain bodies of enormous mass. Some of them are many hundreds of times larger than the, heavier than the sun, but we do not experience any force from those stars, because we are so far away, hundreds of light years away, thousands of light years away, we do not experience any force. So, for example, if a body is moving, or if you look at our solar system itself, if it is moving, we do not care about the potential energy. We will worry only about the kinetic energy and the potential energy of the neighboring forces. We do not worry about that, because that is redundant. So, by the same token, if I imagine that this mass were to be at rest far, far away from this small mass, it is not experiencing any force. Therefore, it does not even recognize the existence of this body as far as force is concerned. I may see a brilliant object, but it has nothing to do with me. And therefore, if it is at rest, I will say the total energy is equal to 0. And for example, if I connect it to a spring, I will say its kinetic energy is half kx squared. I don't have to worry about whatever this residual potential energy is, because it is so far away, because the force is not to be worried about. Therefore, if I write my total kinetic energy is equal to half mv squared minus gmm by r. So, I should not use the word notation T, I should use the notation E, because we have used T for kinetic energy. What we are saying is that we have employed the constant such that at r equal to infinity, body at rest has 0 energy. So, this is the constant that we have employed. Otherwise, you could have jolly well added a constant V naught, and this V naught is an unnecessary baggage. Everywhere it shifts the energy by a overall constant. So, this essentially restates what you already know, and what is that? All energies are measurable only up to a constant. Only energy differences make sense. Absolute energy is of no interest to us. That is something that we should remember, and this is what we have employed. So, now I am given the total energy in a gravitational field to be, let me repeat, my half mv squared minus gmm by r. So, I invite you, although I told you what the result is, to verify, please verify that dE by dt equal to 0 implies Newtonian law. Implies Newtonian law of gravitation, and therefore, it is very, very convenient to use this concept of energy, because as people often put it, while force is a vector with 3 components, energy is a scalar, and it is always easier to deal with scalars than with vectors. And when I do the differentiation, and if I know how to keep track of directions, we will learn about that later, you can always get what the force is. So far, I introduced the concept of a potential energy of a smaller mass in the field of a larger mass. It is really not required, because if you go back and if you look at this force equation, now where is that? So, here it is. If you look at this force, I wrote the force exerted by the larger mass on the smaller mass. Maybe it is not very clear. So, let me write big letters, larger mass on the smaller mass. If I want it on the force on the larger mass by the smaller mass, what will I do? I will again write the equation, but the direction of r will be unchanged. So, this unit vector r always gives the radius vector from the object to the object on which the force is acting. So, if you remember that the potential energy is the same, it is only the way we define the unit vector. Is it from A to B or from B to A? That is what tells me whether I am looking at the force acted on A by B or B by A. You are getting the point, right? That is what we are doing. If we did that, what I can now do is to consider collection of masses. Collection of masses and see what we get. So, in discussing this particular problem, I am going to make use of one more very, very important principle, which you will encounter even in electricity and magnetism. And what is that? That is the principle of superposition. The forces add up. I will make a few more statements about that in a while. So, what we shall do is to look at various masses, bodies. Okay, this is my coordinate system. So, this has a mass m1, this is a mass m2, m3, mk, and let me call this as, I am going in this direction, Mn. So how many bodies are there? N bodies of respective masses M1, M2, M3, Mk, Mn. So if I write Mk, k goes from 1 to n. Now each of these bodies interact with every other body through the gravitational force. That is the principle of superposition. So if I were to ask you to write down all possible forces, how many equations would we write? There would be n equations of motion. So I am interested in M1. So I will write M1 d V1 by dt, that is the force, is equal to minus g M1 M2 by R12 squared unit vector M1 M3 etc. And the right hand side will have n minus 1 terms. This is my force equation, n equations with n minus 1 terms. No body will act upon itself. It is always acted upon by other bodies. That is our assumption. And this statement that n equations of motion is what we have is also a misnomer, because each equation is actually a collection of 3 equations, because it is a vector equation. Therefore, let us be more honest and let us write 3n equations of motion. So you have to keep track of all that, and you should not make any mistake, and you should write that. How would it look like if I were to write the same thing in the language of potential energy and kinetic energy? So let me repeat that again. So I have, let us say, these bodies. I have shown 1, 2, 3, 4, 5, 6. So this is M1, this is M2, this is M3, this is M4, M5, M6. Then what I will do, I will connect this, I will say the distance between them is R12, the distance between M4 and M5 will be R45, R12 is equal to R21, R45 equal to R54, or more generally, distance between Mi and Mj, I not equal to j, is denoted by Rij. The principle of superposition of forces translates into the principle of superposition of potential energies. So that is what we have. Therefore, how will I write my total energy now? If there are n bodies of masses M1, Mn, then my total energy Et is half I equal to 1 up to n Mi Vi squared is what I have. If there are 2 bodies, there is only one potential energy term. I should not repeat that, because it is a potential energy between those 2. And depending on how I differentiate, I get the force that is on 2 because of 1 or 1 because of 2. That is something that we have to remember. In a similar manner, if there are 3 bodies, how many such pairs are there? 1, 2, 2, 3, 3, 1. There will be 3 such pairs. And more generally, if there are n bodies, there will be n choose 2 such pairs. We should not overcount. And we know how to do that. There are many, many ways of writing that. Is that okay? Now I am going to write my potential energy. So maybe I can pull the G out, but that is not required. So one way to write that is put I not equal to j and put a half. This half takes care of double counting. 1, 2, 2, 1. They are both the same, therefore I divide it by equal to 2. Or another way of writing is to simply write I less than j. There is no problem at all. So if I start with 1, I'll get 1, 2, 1, 3, 1, 4, 1 n. Then 2 will start with 2, 3. Therefore, 2 n will not be counted. Either way it can be written. And this will be G mi mj divided by Rij. This is how I write. So please remember, Rij is the distance between mi and mj at that particular instant. Now of course, if I take these bodies and leave them, even if they are at rest, what will happen? They will start moving because they will start all attracting each other. So what should I write? I should put a T here and I should put a T here. So at any given time, my total kinetic energy is a function of time because the velocities of each of these particles is changing as a function of time. Because the velocities change, the distances between them change. So that becomes a function of time. Because the distances between them change, the force changes. Therefore, my velocity changes. That is how the cycle closes by itself. So this is a function of time, this is a function of time, and what are we asserting? We are asserting that this is independent of time. This is independent of time, and this is the first quote unquote non-trivial statement of the conservation of energy in a dynamical system where we have a very, very large number of particles, and this is a very important principle. We are going to put it to many, many practical uses when we look at escape velocity, satellites, so on and so forth. But before I do anything, I want to show how this is a very good bookkeeper. Conservation of energy, law of conservation of energy is a good bookkeeper. In fact, this was recognized even more by people who do thermodynamics than people who do mechanics or cosmology at that particular time. Because if you remember the first law of thermodynamics, what does it state? It essentially states that the total energy is a conserved quantity, and there of course the energy is much more than kinetic or potential. It can be any energy, internal energy, chemical energy, depending on what the system is. It encompasses all kinds of energy, but even for us it is a very good bookkeeper even in this limited context. So let me explain. As I told you, if you give me two masses, then and let us say I know the initial velocity of mass m1 and the initial velocity of mass m2 and the initial distance between the two of them, then the subsequent motion of m1 and m2 can be completely solved in Newtonian gravitation. That is the famous two-body problem. In your examples, what we did was to make one of them infinitely heavy, but even otherwise it can be completely solved, as I told you, by using what is called as the reduced mass. So please take my word at that, or go and look up a good mechanics book, you will understand in about 10-15 minutes. Now a very interesting question occurs, what happens if I have three masses? m1 is free to move, m2 is free to move, and m3 is also free to move. There is no condition on them. There is no condition on the motion, there is no condition on initial velocity, there is no condition on initial position. So that is what I have. So what will I do? The initial separation is r13, this separation is r23. Of course, I have written it in a plane, they need not lie in a plane, they may lie anywhere. And this mass 3, m3 has a velocity v3, and everyone knows that it is child's play to set up the equations of motion, because I told you how to do it for n bodies. What can be done for n bodies can be specialized for 3 bodies. Setting up an equation is one thing, solving the equation of motion is another thing. After all, even in this limited context of 2 bodies, you looked at only circular orbits, whereas the Keplerian orbits are all elliptic. We still do not know how to do it. So a big question arises as to how to solve the motion of three bodies. So imagine that I have the Sun, the Earth, and also the contribution coming from Venus. Venus is the nearest planet as far as the Earth is concerned. Suppose I want to solve this problem. This problem is what is called as a three-body problem. And mathematicians and physicists spent centuries trying to solve this problem. They tried many techniques. Whatever you do, you are not able to get solutions which are stable. That is, if you make a small change in your initial position or velocity, you would not be able to predict what is going to happen later. This was a big problem until the end of the 19th century, when Poincaré actually conclusively showed that it is impossible to solve this problem. When I say that it is impossible to solve this problem, you should understand what I mean by that. By that I mean, you cannot get closed form solutions. You can always solve it numerically, but your numerical solutions will be valid only up to a certain time t. You should understand that it is valid only up to a certain time. After that, your approximation will break down. Then you will have to make even a more refined numerical calculation. Even that will break down, so on and so forth. Basically, we don't have a robust mechanism, numerical method either, of solving this particular problem. So we do not know how to solve this problem. So what is the role of the conservation of energy? So now I will say, these three masses are given at certain time t equal to 0. So there is a velocity v1, v2, v3 at time t equal to 0. So you have r12, r23, r31. We can at least ask the question if at a later time this configuration is possible, let us say. So I will draw these lines. So my mass 3 is here, my 1 is here, and 2 is here. So what happens? So I will again give velocities v1 bar, v3 bar, v1 bar, v2 bar, and this will become r12 bar, r23 bar, and this will be r13 bar. This is the new distance. At a later time, at least I can find out whether the total energy in this configuration is the same as total energy in this configuration. If they are not there, if they are not the same, even though I do not know how to solve the equation, I can be confident that this configuration is impossible. So conservation of energy at least allows us to rule out impossible geometries, impossible states. Now what if the total energy here is the same as the total energy there? Now you can do a little bit more analysis, and then you can try to find out whether the solution is possible or not, but at least we have reduced the total number, that is the number of trajectories or the number of configurations that are possible. In a similar manner, you can calculate the total angular momentum. That will put one more condition, because the total angular momentum is a conserved quantity. You can look at the total momentum of this three body system. You can look at the total momentum of the three body system. So how many constraints are we getting? Total energy, 3 components of total momentum, 3 components of total angular momentum. You put all these constraints, you can try to solve for the equation for lesser number of coordinates. Is that right? So that is something that you can do with a very great efficiency. You don't have to solve for all 9 components. R1 has 3 components, R2 has 3 components, R3 has 3 components. You don't have to solve for them. You can eliminate a large number of variables by these constraints, go to smaller number of coordinates. This in fact is the idea behind many problems that you solve in mechanics later. Therefore, conservation of energy is an excellent bookkeeper, because it tells you what is not possible, even if it cannot tell you whether something is possible or not. So this is one of the great advantages of this. Now as a second application, what I shall do is to look at a very favorite and a familiar problem for all of us, and that is escape velocity. which is a stuff made of dreams of human civilization for ages. Human beings not only wanted to fly high in the air like the birds. Da Vinci made many models in order to fly, but human beings also imagined what it would be if you could actually escape from the earth. There are so many myths. So the Greek mythology has the myth of Icarus. I don't know how many of you know. So Icarus was a very powerful king. So he made himself wings, okay, which could flap very hard. Okay, those days people did not know how far the atmosphere extended. Is that okay? So, and then he started flapping the wings, those artificial wings, and it started going higher up and higher up. He escaped away from the earth. I think he had an engineer or a designer who made the wings for him, who had told him, don't go too far away from the earth, don't go too near the sun. But Icarus was very ambitious, so he kept on going nearer and nearer the sun. So the heat of the sun melted the wax and the wings collapsed, and this guy came crushing down. In our own country, we have the story of Jatayu and Sampati in Ramayana. They were brothers. So the two brothers started flying high up in the air, and they escaped from the earth. And when they were reaching the sun, the scorching heat of the sun started burning them. The elder brother, who was like a father figure to his younger brother, protected the younger brother. So the elder brother Sampati collapsed, and he had lost the power of his wings, but Jatayu survived, and he later on played a very important role in story of Ramayana, as you people know. So the big question that we want to ask is, suppose I want to throw an object at a certain height, what should be the minimum velocity? Right? Because I want to send a plane higher up, and then I want it to go in a circular orbit, or I want to launch a rocket, or I want to send some other thing which will look for alien human beings, maybe in faraway galaxies and stars. So basically, that is the idea behind escape velocity, and the principle of conservation of energy tells you a very simple answer, and let us see how it works out. So let us take the surface of the earth, and then there is a body here, and it wants to escape away to infinity. So here, what is the total energy according to what we have written? The kinetic energy plus gravitational energy, which is minus g, mass of the earth, mass of the object, divided by the radius of the earth. That is what I have. Now, what is the minimum energy that I should supply this body so that it can reach here? After that, you can supply excess energy. What is the minimum energy that I can supply? If it had excess energy, that means even at infinity, it would have had more energy than being at rest. So the minimum energy that is required is that, for escaping, is that this is equal to 0. Because we said that an object at rest at infinity will have 0 energy. So the bare minimum energy that is required for the object to escape from the surface of the earth will be given by half m, I will put the notation escape, is equal to minus gmm by r. So if we substitute, what are we going to get? We are going to get V escape squared is nothing but 2 gme by re, which you see is a highly non-Aristotelian expression. We think that if you want to throw an elephant up, it should have higher velocity rather than for example, a small piece of ball. That is not true. The escape velocity is the same, but the energies are different. For the same VES, an elephant would have much more kinetic energy than the small ball. So this escape velocity is independent of the mass. So my V escape is given by root 2g me by re. It is more convenient to express this expression like in your textbooks in terms of a quantity that you are all familiar with, and that is g, acceleration due to gravity. So how do we get that? You write mg is equal to gme m by re squared. So m cancels. So gme by re is re into g. Therefore, V escape is equal to root 2g re. This is my escape velocity. You could also do it from the force expression, but it would not be conceptually straightforward. You have the concept of an energy and you are conserving it. So here the total energy was shared between the kinetic energy and the potential energy. It is so shared that the particle is at rest at infinity, but at infinity the force is equal to 0, therefore the particle has escaped. So strictly speaking, we should write V escape is root 3g re plus some small epsilon, some small velocity. Otherwise, this velocity is critical. If it is slightly less than that, it will come back. If it is slightly greater than that, it will not come back. That is something that we have to remember. So therefore, we will add a small epsilon. It is a small increment. Greater than that, it is like when when an object is on a maxima, it is an unstable equilibrium. Even the smallest perturbation will do that. That is what we say, and that is what we have. So that is what we have established. This is your escape velocity. And this was the great challenge, because we will see how large it is. So there are some numbers. So let us say g is something like 10 meters per second square, and radius of the earth is 6400 kilometers, which is like 6400 into 10 cubed meters. So if you plug it in, your V escape turns out to be something like 11.6 kilometers per second. Kilometers per second is what you are going to get. That is your escape velocity. So if you want to know how big a number this is, please multiply it by 3600, because that is what we are used to when we look at vehicles that move on the earth or aeroplanes that move high up in the sky. So we are speaking of 11.6 into 3600 kilometers per hour. So that is close to something like 40,000, I don't know, kilometers per hour. 36 into 11, 36, 10 is 360 plus 36, 396, there is another 6, actually greater than 40,000 kilometers per hour. That is what we have. Whereas the fastest of the airplanes, at least the usual airplanes that we take, move with a speed of about how much? 700 kilometers per hour, 800 kilometers per hour. That is the kind of speeds that they have. There are planes which move with a speed greater than that of speed, up to 7 Mach. The speed of sound in air is about 300 meters per second. So it goes with a speed of 300 meters into 7, let us say 2100 meters per second. That is only 2 kilometers or 2.3 kilometers per hour. These very, very fast planes which create shock waves and all that. Even that is very short compared to this 11.6 kilometers per second. In fact, one speed that is comparable to this speed is the speed with which the earth is going around the sun. It is about 30 kilometers per second. But then that is a different matter. It is a freely falling body in the field of the sun. So this is not easy to achieve. And that is the reason why we had to wait for a long, long time as far as technology is concerned in order to attain these speeds, and this is what we have. This was not calculated under any assumption, because I simply equated the total initial energy with the total final energy, but there are some corrections. And what are these corrections? These corrections are whether I launched the rocket high up in the air perpendicular to the surface, or at an angle, or at a tangent. There are differences. You may wonder why there should be a difference, because when I wrote this equation, Although I indicated the distance in a direction perpendicular, this RE doesn't care in which direction I went. I could have written it this way or whatever. In whichever direction you go to infinity, my total kinetic energy is always, your potential energy is always dmm by RE, irrespective of the direction. Therefore, you must be wondering why I am showing different directions. It is small but not insignificant, and that is because the earth, that is how it is, rotates about its axis. For simplicity, let us not make a distinction between the axis of rotation and the geometric north pole and the south pole, whatever it is. So let us assume that it is rotating. Because of the rotation, there is a centrifugal force. I should be extraordinarily careful. There is a centrifugal force in the frame fixed to the earth, and centrifugal force is radially outwards. Because it is radially outwards, it is acting in a direction opposite to the direction of the gravitation, and therefore depending on in which direction you shoot your body, the escape velocity is going to change. If I shoot it perpendicularly upwards, there will be the maximum decrease in the escape velocity. If I shoot it tangentially, then there is no decrease at all. We will discuss that in the next class. We have run out of time. And I will conclude the lecture. This was not to be the last lecture on gravitation, by giving applications to various artificial satellites. And India is one of the countries which is a leader, in satellite launching, and it uses incredibly intelligent and sophisticated technology. Probably we will spend some time on that also. Until that time, please revise. Have a good